Hello, this is Tara from E12. This is going to be my video observation report for Digital Systems Laboratory lab from Valencia College. The lab that we are working on today is going to be Lab 8. It's dealing with the JK flip-flops, which are these right here. So this is the pinouts for the JK flip-flops. Please note that on pin 5 is where power comes in, and pin 13 is ground, and the other pins are going to be your inputs and outputs. Through this video, I will be going through these items: the objective, materials, background, procedure, data and observations, and answer the lab questions, and possibly come up with a conclusion. Now, if we go to the board, this here is the JK flip-flop, and as we have in the diagram right here, do you notice that there's this little notch, and then we have a notch here? That is to help you line up where to find your pinouts and where your VCC and ground are. Now, on here in the lab manual, it says the objective is to test and troubleshoot a NAND latch flip-flop. So the items that we would need was a 7476 and a 7404. Although I found that I didn't, well, actually I did need a 7404, but it's this one right here. That's a 7404 chip. Unfortunately, I don't have the pinout diagram, but the last pin over here is going to be the power, and this one over here is going to be ground. Pin 1 is in, pin 2 is out, so odds are going to be in and evens are going to be your outs. Your 7406, the breadboard, well, of course we don't really need a breadboard because we have the beautiful L&Co digital analog trainer model XK150. The procedure, well, actually, the background, which kind of gives you a background, but they're going to want you to rewrite this in your own words. In the background here, it says, in previous experiments, you constructed and examined the operation of combined logic circuits whose output solely depends on inputs, which means that combination of logic circuits do not have any memory capabilities. In this experiment, we will examine logic circuits that their output only depends on current state/condition of the inputs, but also on the previous state. These devices are called sequential logic devices, also known as memory devices. Okay, so now we're going to go ahead and move on to procedure. The procedure here says Part 1 JK flip-flop operation 74LS76, which would be these two chips right here. This one's going to be Part 1 and Part 2, and this one's going to be for Part 3. So it says A, connect J and K flip-flops shown in the figure 8, data switch 1 and data switch 2 respectively. B, make sure that the VCC and the clear inputs of the flip-flop are connected to the VCC. We have done both of these items. Let's connect logic switch A, which is this switch right here, which is, you have A and A naught, and we'll get into reason why we have to use this chip, to the clock input of the flip-flop. So basically, this is going to be acting like our clock, where it flips back and forth, up and down, to represent a square wave. Okay. And let's see, then we have complete the truth table 8.1 to verify the flip-flop operation, which is what we have right here. In this diagram, which is represented with 0, 0, no change, 0, 1, 0, 1, 0, 1, and 1, 1 change. So they're only changing on when it's 1, 1 or 0, 0, but you're only going to get a 1 or a 0 value if J or K are opposite of each other. Going back to the procedure, show the circuit operation to the lab instructor. That I did, which is the reason why I have a signature right here from the lab instructor. Remove data switch 2 and connect the data switch 1 to J input and the input of the inverter as shown in figure 8.2. So that would be figure 8.2. Now this makes it behave as a D flip-flop where both inputs are connected to the input and output of the 7404 chip, which is going to be the inverter, which is also the representation for the NOT gate. Remove data switch 2, connect the switch to data switch 1 and the J and the K input of the inverter as shown in figure 8.2. Connect the input of the inverter to the K as shown in 8.2. Complete the safer table in 8.2. The circuit behaves again as a D flip-flop. That actually counts as one of the lab questions. So here is the output for Q and J. So we have here that when J is 0, the Q output is 1. When J is 1, the output is 1. Okay, so now we can go ahead and move on to part 2. In part 2, we're going to work with the JK flip-flop mode. Actually, let's roll back just a little bit because I want to demonstrate to you on the board as far as this JK flip-flop acting alone by itself, which I believe I still have hooked up right here on the board. So over here we have this one as the one. We're going to go ahead and turn off 8.2 and 8.3. And we're just going to go ahead and flip these switches. And we'll notice that on 8.1, which is this one switch right here, that it's only changing on the up. So when it's A again, A naught, A naught, A naught, A naught. Another interesting thing that I could plausibly do is hook up this to the square wave of the frequency generator on our breadboard, which would act like our clock. We could plug it in right here at 60 megahertz, but unfortunately at 60 megahertz it is no longer visible to the naked eye. So what I'm going to do is remove this JK flip-flop. Oh, I just bent my pins. I'll have to straighten those out later. And plug it into the and then run to ground. Actually, no need to run to ground. Just take the wires and plug them into the frequency generator over here. Now, I'm pretty sure you can make it out that light is blinking, but it's at a even at the lowest setting of the frequency generator, it blinks really fast, almost not visible for the human eye to make it out. And just to prove my point, we're going to turn up the frequency. Oh, actually, yep, turning up the frequency makes it almost seem like it's a constant. But turning it down, and we begin to notice that it's blinking again. It seems to be becoming more evident somewhere between 1 kilohertz and 200 kilohertz. Alright, so we're going to go ahead and connect this back to our switch A. Now, I know this looks like a giant spaghetti monster, but believe me, it is. Alright, so now to demonstrate part 2 with the JK flip-flop. So we're going to set 1 down. Actually, we're not done with the JK flip-flop. So on here on the board, I have this labeled as K and this one as J. So when they're both up, it only changes to 1. But when they're down and we flip the switch, when they're both down and we flip the switch, we get no change at all. But when our K is up, which is our one switch right over here, and we flip the switch, we get a 0 output. When we reverse that, when it's J high and K low, and we flip the clock, there is absolutely no change. But only when we have it on 1, where J is 1 and K is 1, well, it would certainly help if we had. Okay, so we're going to redo that truth table on figure 8-1. So 8-1, we're going to have it both be 0. And we're going to flip the switch. In fact, just to make sure that this is working, I'm going to set them both to 1. And there you go. So that is working. Alright, so now that that light is off, I'm going to set it to 0, 0 and flip it. And we don't see the light changing over here. So that light's not going to change. So now we're going to flip it to 0, 1. And we're going to flip the switch. And there is absolutely no change, but we're going to say that that's 0. Now we're going to reverse it where J is 1 and K is 0. And we're going to flip that switch. And we get a 1 output, regardless of what the clock is doing. And then again, we're going to go with 1, 1 on J and the K. So J is 1, K is 1, which is the on state. And we're going to flip the switch up and down. And we only get a change when we're at A. Not. It's only changing on A not. Okay, so it's only changing when it's on A not. Alright. So now I feel confident that we can go ahead and move on with part 2. I'm going to go ahead and turn off our J and K on 8-1 so that we don't get confusing readings, and that way the light for that one stays off. So now we're going to move on to 8-2 and demonstrate to 8-2. Now on the breadboard and pencil, I have labeled this one as 8-2. That's going to be switches 4 and 5. And when J is the only one that is actually hooked up, which is going to be switch 5. So So when J is 0, it remains 0. But when J is 1, it turns on, which means it's a high state. Okay. So in part 2, it says connect to the. In part 2, it says connect the circuit as shown in figure 8-3. And 8-3, it's asking you to hook up 2 flip-flops. Connect all J and K inputs to VCC, which is pins 5 and pins 13. 13 being ground, pin 5 being the VCC where you're going to get power. Connect the pre-inputs of each flip-flop switch to switch 1 and connect the clear inputs of each flip-flop to switch 2. Now I ended up doing this in Multisim before building it out and having Multisim actually using Multisim to show me how to properly build this circuit, which I will be more than happy to post with this video. Set both switches to high. So we're going to set both switches to high. So this would be switch 1, and this one's going to be switch 2. We're going to set that to high. Now, this is what happens when you set both switches to high, and you flip the clock. Okay, so it says switches both to high. Connect the clock to input A on the breadboard, toggle the switch A 5 times, which we just did, and then complete the truth table in 8-3. So I'm going to go ahead and show you the truth table that I have here in 8-3 and explain it to you. So this right here, in the first one, it says clock pulse, and then 0. You're going to, on the QB, you're going to get 0. And then you're going to get QA, 0. So this is basically completing a truth table. So on the decimal count here, now believe it or not, this is a 3-step counter. So let me get it to 0. So that's 0, 1, 2, 3, 0. Now to get to the questions. It says here on J, in the space below, write down your observation. Okay, so it says here, remove the connection from switch A and connect it to switch 3. Toggle the switch 5 times and observe the state of the LEDs. So we're going to do that. We're going to remove this, and we're going to move it to this switch 0 over here. And we're going to do this a couple times. Now, there is no change when we use A and A not logic switch. Change only occurs on A not or 0 or on an off state. The same is true for switch 0 or switch 3. So let's do that with switch 3. Okay, so let's go ahead and we're going to go ahead and toggle the put it back. Oh, actually, it doesn't say to put it back. It doesn't say to put it back. Okay, so now it says toggle the clear input of the flip-flop. What will happen to the output of the flip-flop B? Okay, so we're going to pull that out. Oh no, we're going to leave it there. 1, 2, 3, 4, 5. Haha. Okay, so toggle the clear input of the B flip-flop. So in 8-3, we're going to toggle the clear, which is pin 7. We're going to toggle the clear input of the flip-flop low. What will happen to the output of the flip-flop? So we're going to go ahead and toggle switch 3. And the answer that I have placed here is that it stays off, and it no longer counts to 3, because setting the JK flip-flop pins 6 through 12 to ground sets it to a low state. So what I did is by turning switch 3, setting the clear to a low state and turning it off, sets it to ground, and it won't make any changes at all. Okay, so after that I got the lab instructor's signature right there, and then we're moving on to questions, which I had not finished. Okay, so the questions that I have listed here is, why is it important to use a debounce switch like switch A as the clock input? Okay, so the way this was explained to me, in fact, let's grab the whiteboard and a few markers. So the way this was explained to me was that when you use a debounce or a logic switch, it helps if you have a good marker. When you use a debounce switch or a logic switch, the signal is steady. But however, if you use a regular switch, like one of these switches over here, what happens when it's in an on state is it'll go up into an on state, and whenever it's on in an on state, it'll bounce up and down like this, and then it'll go straight down and have a smooth signal when it's off, and then again when it's on. Now in the JK flip-flops and any other flip-flop, this could cause a false signal and cause a misfire. So you wouldn't want that to happen. So in my answer for question A, why is it important to use a debounce switch like a switch A as the clock input? Logic switch A0 has a steady on-off state, as where the regular switches bounce on and off on a high state. Now in figure 8-3, the J and K inputs are known as synchronous inputs. And question C, in figure 8-3, the pre and clear inputs are known as asynchronous inputs. In figure 8-3, the flip-flop's outputs Q will respond to the J and K input level of only at the falling edge of the clock, or at a 0 state. Now we're going to go to the back side, and that's when I realized that we were complete with this lab. In conclusion, this lab was pretty fun. I actually have a really good idea on how to make a counter, and I do believe that it is now possible, seeing now that I have 3 JK flip-flops, that I could possibly make a 4 counter, maybe even a 5. Further experimentation will be needed. Anyways, rubber duckies, and the reason why I call you my rubber duckies is because I'm learning this, and in software engineering, when you're trying to debug code or debug or solve a problem, you explain it to your rubber ducky out loud, line by line. And that's pretty much what I'm doing here with the electronics. So, thank you, my rubber duckies. If you have anything that you disagree with any of my answers in my labs, please feel free to leave a comment below and tell me the reason why you think I'm wrong, or if there's something wrong with my observations. Or perhaps maybe you ran this experiment yourself and got different results. Anyways, bye!